Let's begin with mass. Mass, the amount of inertia an object has, given in kilograms. Inertia, the amount of resistance an object has to acceleration. Remember that Yana has more mass and thus more inertia than Jessica, so she should be harder to accelerate. We will now demonstrate this using trampolines. First, we start with Jessica. Take note of how high she bounces. Now we have Yana. See how much less height I'm able to get than Jessica? This is because I have more mass. Now let's do a side-by-side comparison where you can really see the difference. Jessica gets higher because she has less inertia, so it is easier for her body to accelerate upwards than it is for mine. Now it's time to move on to volume. The amount of space an object takes up, measured in cubic meters. Let's start with this regular balloon. It takes up a relatively small amount of space, so it has a small volume. But when I blow it up, I've increased its volume because it now takes up more space than it did before. See? And that's volume. Now, it's time for weight. Weight, the force of gravity exerted on an object, measured in newtons. Here, we have a picture of Mount Everest. Because gravity gets stronger the closer you are to the center of the Earth, someone on top of Mount Everest would weigh less than they would at the shore of the Dead Sea, since the Dead Sea is a lot closer to the center of the Earth. The person's mass hasn't changed. They still have the same resistance to inertia. But because the force of gravity changed, the person's weight changed as well. Now, let's move on to Newton's first law. The law states that an object will not accelerate unless an unbalanced force acts on it. However, the law is more commonly known as an object in motion tends to stay in motion, and an object at rest tends to stay at rest. However, the common misconception about this law is that an object needs a continued force to stay in motion. This is false. An object needs a net force of 0 acting upon it to either stay at rest or stay in motion in a straight line at a constant velocity. The only change that can occur is acceleration if the net force changes in one direction or another. Now, let's go bowling. We take a bowling ball as a prime example of Newton's first law. Once the ball is set in motion, it remains in motion at a constant velocity in a relatively straight line until it hits the pins and then falls off the edge of the lane. If the pins and the edge of the lane weren't there, the ball would likely continue straight. Here, we have a ball that is at rest. It remains at rest until Jessica gives it an applied force that makes it roll over to me. Why do you push harder on the pedals of a bicycle when first starting out than when moving at a constant speed? Alyssa will now demonstrate this for us. See how hard she's struggling to get the bike moving? But once it starts going, she just rides easily. The explanation for this is that Alyssa has to push harder than the force of friction in the beginning to get the bike going. But once she gets it going, she only has to pedal as hard as friction to keep it going at a constant velocity. Thanks for watching.